That's right, folks. There really is a little bit more to it. So tonight's lesson again, stoichiometry. What we're going to take a look at are some specific ideas that are mathematical tonight. You need some skills being able to solve stoichiometry problems, either using a method that we call dimensional analysis, or maybe even that method that we call ratio proportion. It's really up to you as to which strategy you prefer to use. So before we get started, let's have a little fun. As you know, been sharing a few jokes with you. So why don't we get to our joke for the day? So what was it that the thermometer said to the graduated cylinder? Well, what he said was, "You may have graduated, but I've got lots of degrees." All right, let's get underway with our lesson tonight. So tonight's lesson is coming to you with two goals in mind. One of them would be to be able to identify the limiting reagent from quantities of reactants that are given. The other would be able to predict amount of product, knowing that we were going to run out of one of those chemicals, and we would be able to predict the exact amount of product because we've run out of one of our reactants. So it's got to become mathematical. As long as you have some skills with stoichiometry, either using the strategy that we call ratio proportion or dimensional analysis, it's actually not that complex. It's just looking at the idea of stoichiometry from a little different perspective. Okay, so if you recall, there was this analogy where we looked at there being two quantities that we start with, car bodies versus tires, and there's a very specific ratio. One car body needs 4 tires. That makes a car. And we continued using up car bodies and 4 tires until we ran out of something. So cars were manufactured, and what we learned was we ran out of bodies, and we found out that that limits our ability to make any more cars. So therefore, we called our car bodies our limiting, and we called our leftover tires our excess. And what we're about to take a look at is how we might think about chemicals, sort of from the same perspective, but looking at the quantities like mass or perhaps even the volume of a gas. So here we have a particular chemical reaction. We want to focus on what we call the reactants. The whole concept is centered around understanding that there's something called the limiting reagent, which is always on the reactant side. Whichever one of these two chemicals we run out of first, that's going to determine when we stop manufacturing product. So we want to actually use stoichiometry. We're actually going to find out we have to use stoichiometry 2 times. So twice. We're going to use stoichiometry for the amount of one reactant given, turn that into a product. We're going to do the same thing with the other amount of reactant given, turn that into the same product. So let's get started with a little bit about how that works. So here's a little context. Let me get rid of my face because I find that very distracting, as you probably know by now. That's much better. So when we look at this, there's a context here, and it's an interesting one. This basically says that when we use this thing called the airbag, there's a chemical reaction that occurs that allows the airbag to inflate. And one of the byproducts of that initial chemical reaction is a chemical known as sodium, a highly reactive metal. And if that sodium were to get into your eyes, the moisture on the surface of your eye, that could produce like a physical burn or even a chemical burn as well, and damage the eye tissue. So engineers have come up with a way to kind of work around that by adding another chemical to consume that sodium to make the deployment or the release of the airbag safer for the drivers and the passengers. I just wanted to give you a little context because sometimes I think context is important to understand that chemistry has use. So let's get rid of the context because that's going to be very distracting. Okay, so really there's this question here kind of comes in 2 parts. They want us to determine what the limiting and excess reagent, what the limiting reagent is given these 2 quantities. We have sodium, Na, and potassium nitrate, KNO3. What I like to do is I like to label the exact amount. So it says there's 32 grams of sodium. It says there's 76 grams of potassium nitrate, our reactants. These are the two piles we have available, very similar to having car bodies available and tires available. So what we do then is we just kind of figure out which of these products are we most interested in, or which one would we like to figure out the quantity that these reactants could produce. So you can actually choose whichever product you want. I might make a suggestion to see if there are multiple parts to a question like this one has. It asks what volume of nitrogen gas would be released. So I think our quantity that we're interested in here is X number of liters of nitrogen. We're going to use stoichiometry to take 32 grams of sodium and see how many liters of nitrogen that would produce. Then we're going to do the same thing and figure out how much nitrogen gas, 76 grams of potassium nitrate, could produce. Once we've done that, we'll have a very simple strategy for knowing which of these is the limiting reagent. So let's get started. We're going to start with our dimensional analysis method. We write down the given quantity. Again, let's start only with our sodium. We'll later go back to this potassium nitrate. So we're interested how many liters of nitrogen 32 grams of sodium could produce. So the first thing that we would do with dimensional analysis is we would take our sodium amount and turn it into a mole amount so we could use the mole ratio later. So we will turn this into a mole amount. By knowing the amount of sodium, its molar mass, that allows us to convert from mass to a mole amount. So we apply the molar mass. This should actually read grams down here. So let's change that so that we know that we're doing this correctly. So this should read the number of grams, not the number of moles of sodium here. So this will be a G for gram. There we go. What that'll do is that'll cancel out the gram amount, and that will make a mole amount of sodium. So the molar mass for sodium, 22.99 grams. What we do next is we take our mole ratio. We convert our given chemical into our desired chemical by using the mole ratio. Well, that mole ratio comes from the balanced equation. There are 2 moles of nitrogen, which is what we desire, our X. For every 10 moles of sodium are given. We get rid of our given, we turn it into desired. Notice we've turned it into a desired mole amount, however, and we really desire the number of liters. So we're going to add that step to turn the mole amount into the number of liters. And as you know, there's 22.4 liters of any gas, as long as we assume that gas is at standard temperature and pressure. We now are able to predict the exact volume of nitrogen that this could produce because we have canceled out the mole amount and produced a quantity of 6.2 liters of nitrogen. So 32 grams of sodium, the most nitrogen it could ever make would be 6.2 liters. It would be completely used up to produce that amount. What we're going to do next is we're going to take that other reactant right here called potassium nitrate, and we're going to do the same sort of stoichiometry. We're going to predict how many liters of nitrogen that could produce. So we'll start by writing down our given, 76 grams of potassium nitrate. We'll turn that into mole amount by using the molar mass. The molar mass happens to be this 101 value. Next thing we do is we use mole ratio to turn it into the chemical we're interested in. Well, we're interested in nitrogen. Turns out that the mole ratio now is 2 moles of nitrogen for 2 moles of KNO3, So 2 moles of nitrogen for 2 moles of KNO3. What that does is that now produces the mole amount of nitrogen. And just like we did up top, we can turn that into a volume because we know there's 22.4 liters of nitrogen for every 1 mole. What this does is this produces the volume of nitrogen gas that 76 grams of potassium nitrate is capable of producing, and it turns out to be 17 liters when we do our math. Review that we would just take 76, divide by 101, times 2, divide by 2, times 22.4. Next, we make a choice about which of these chemicals, either the sodium or the potassium nitrate, is the limiting reagent. Well, the simple way to make that choice is the one that produces the lesser quantity of product. In this case, it's going to be nitrogen. That would be our limiting reagent. So we say sodium is our limiting reagent because it makes less nitrogen gas. 32 grams of sodium only makes 6.2 liters of nitrogen. Counter to that, the potassium nitrate, 76 grams of that makes 17 liters. So we would run out of sodium first. Na, or sodium, becomes limiting. Let's look at the procedure or the process using that other strategy we call ratio proportion. Remember, when you set up ratio proportion method, you always make two fractions. First fraction, given over desired. So we're going to start with our sodium amount, reduce what volume of nitrogen that could produce. Just like we did in this top example for dimensional analysis, we want to see what volume 32 grams of sodium could produce. Next thing we do, on the right side, our fraction, the labels match. Grams of sodium, liters of nitrogen, liters of nitrogen. So these are the amounts equal to 1 mole, and that's how we set up that second fraction, the amounts equal to 1 mole. Next thing we do is we add the mole ratios in. Well, for sodium, there's 10 moles. Coefficient is 10. For nitrogen, there are 2. Coefficient is 2. Next, we cross multiply. X times 10 times 22.9, 32 times 2 times 22.4. Once we do that, it turns into an equation. We get the equation in this form. We can divide each side by 229.9. Lo and behold, we get the same value we did with dimensional analysis. 32 grams of sodium produces 6.2 liters of nitrogen. Let's do the same thing with our potassium nitrate. Our given over our desired, we were given 76 grams. We desire to know how many liters of nitrogen that would produce. On the right side, the fractions match, but we put the quantities equal to 1 mole. 1 mole of KNO3, the molar mass, 101.11 grams. 1 mole of nitrogen, because it's a volume, the 1 mole of volume is always equal to 22.4 when the volume is at standard temperature and pressure. So we have quantities equal to 1 mole. Now we apply mole ratios. 2 moles of N2, 2 on the bottom. 2 moles of KNO3, 2 on the top. Next, we cross multiply, turns it into an equation. X times 2 times 101.1, 76 times 2 times 22.4. Equation, divide each side by 202.22. Looky there, we get 17 liters. So our choice, whichever one produces the lesser quantity, in this case, it was the 32 grams of sodium. Sodium is our limiting. So we kind of have an answer to 2 questions, in this particular example that we listed here. There's a part A and a part B. So our part A asks for what is limiting. Well, what we can do is we can type in here, Na is our limiting, because we ran out of Na first because it only makes 6.2 liters. It makes less than what the potassium nitrate would be. Second part of the question, what volume of nitrogen gas would be released? Well, whatever volume we calculated, that is the volume that would be released. It can't release 17 liters because when we run out of sodium, the reaction stops. So what it can only produce is 6.2 liters. So in this case, our quantity of nitrogen that it could release would be 6.2 liters of N2 or nitrogen gas? We have an answer to both parts of our question. Part A, sodium is limiting. Part B, the volume that we can manufacture is 6.2 liters because we run out of sodium and the reaction would stop there. Let's take a look at a second example. We'll have to clear this. There we go. Our second example has a context again. If we were going to manufacture an element called iron, what they do is they dig out of the ground an ore of iron. That ore is sometimes called iron 3 oxide. I'm actually kind of sure that they don't call it iron 3 oxide in the steel trade, but in the chemistry trade, that's actually the technical name for it. When they combine that in a furnace, a very hot furnace, with a gas called carbon monoxide, what ends up happening is the iron melts out of the compound and it turns into the pure form of iron. So what we have here is we have a context that allows us to make some predictions. So first thing we want to do is we want to recall that we're only worried about the reactants. Iron 3 oxide, excuse me, it looks like we've got a typo here. So we want to make certain that we think about this as saying iron 3 oxide, not just iron 3, because there really is no such thing as iron 3. So let's just add that. So we'll put it right here, iron 3 oxide. So the amount of iron 3 oxide available is 1,715 grams. So we'll mark that. That's the amount of iron 3 oxide we have available. We'll mark our carbon monoxide. It says we have 890 grams available. Look at part B. It says what mass of iron. So we're probably interested in a mass quantity, a gram amount of iron that these two quantities could produce when one of them runs out. Whichever one of these runs out first, that's going to determine what the quantity of iron is that we could make in grams. So let's start with our dimensional analysis process. Remember, we're thinking of X being our desired grams of iron. So dimensional analysis, we'll start with our quantity, 1,715 grams of iron 3 oxide. We'll turn it into a mole amount first. So turning it into the mole amount, we use the molar mass, Fe2O3, 2 iron and 3 oxygen. That produces now a mole amount. What we do next is we now turn that into the chemical that we desire. We desire it to be iron. We want to get rid of our iron 3 oxide. So we use mole ratio, mole ratio to do that. Our mole ratio comes from the coefficients, 2 Fe for 1 Fe2O3. That allows us to convert into a mole amount of the desired chemical called iron. Well, we don't want the mole amount of iron. We're trying to turn it into the gram amount of iron. So what we do next is we use the molar mass of iron, and that will allow us to convert our mole amount of iron into a mass amount. And we can calculate that. 1715 divided by 159.7 times 2 times 55.85, and we will get a quantity of 1,120 grams of iron. Now we're going to need to do the same thing, figure out if I had 890 grams of carbon monoxide, CO, how many grams of iron could that produce? So we start our stoichiometry over again. Again, what we want to do is turn our gram quantity into a mole quantity. So since it's now CO, we have a different molar mass. The molar mass for CO happens to be 28.01 grams, knowing that there's 1 carbon and 1 oxygen. So what we'd like to do next is turn our given chemical, CO, into our desired chemical, iron. We use our mole ratio to do that. Looks like our ratio in this case it comes from our coefficients. In this case, our coefficients tell us there's a 2 mole of iron to 3 mole of CO ratio. 2 to 3 ratio. What we want to turn it into goes on the top. What we want to get rid of goes on the bottom. Now we would know the mole amount of iron. Now we just turn that into our mass quantity of iron by using the molar mass for iron. So our molar mass for iron, again, is 55.85 grams. And we calculate, and what we find out, when we do this calculation, we end up with 1,183 grams of iron produced. Notice the carbon monoxide produced more iron than the iron 3 oxide did. So the chemical that we started with that produces the least amount of product, in this case, is iron 3 oxide. Iron 3 oxide would make less iron mass. So since it makes less iron mass, it becomes the limiting reagent. We can do the same mathematics with a different strategy called the ratio proportion method. If you're using this method, it starts out with given over desired. We were given a certain quantity of grams of iron 3 oxide. We want to know how much iron in grams that could produce. Fraction on the right matches. We put the quantities equal to 1 mole, called the molar masses. We apply the mole coefficients. 1 mole of Fe2O3, see there's no coefficient here. Assume the coefficient is 1. Iron, the coefficient is 2. Next thing we do is cross multiply. After we cross multiply, x times 1 times 159, we get 159.7x. Cross multiply 1715 times 2 times 55.85. We get a new equation. Divide each side by 159.7. 1,120 grams of iron from the other strategy. Next thing we do is we figure out, using ratio proportion method, how many grams of iron 890 grams of CO would produce. So given over desired, once again, right side, molar mass, right? Since these are both mass amounts, the mass amounts equal to 1 mole. That's what goes in the second fraction. Quantities equal to 1 mole. Apply the coefficients, right? 3 for CO and 2 for iron. Cross multiply, create an equation. 3 times 28.01 times x. We get this form of equation. Divide each side by 84.03. Bada bing, 1,183 grams of iron. So once again, because the iron 3 oxide produces less iron, iron 3 oxide becomes our limiting. And now we can answer both parts of our question above. Both parts of our question above, in this case, what is limiting would be our Fe2O3, or iron 3 oxide. Because that is limiting, that determines how much product called iron that we could produce. This quantity of 1,120 grams is the most that it could produce because the iron 3 oxide would run out. So 1120 grams of Fe is what could be produced. And we have an answer to both parts. So again, limiting reagent, we look at the quantities of the 2 available reagents or reactants that we have. We take those quantities and produce them, or create a product quantity out of them, in this case, iron. And that will allow us to make a choice by knowing which one produces less. Well, it might be a good idea for you to pause before you try this next example. Let's clear the drawings. So our next example is an interesting example. It's about the manufacture of silver from kind of a waste stream or byproducts of the photographic plate trades. Graphic arts, sometimes there's chemical material left over on the photographic plate itself. There's a chemical known as silver nitrate. That silver nitrate is valuable. It has valuable silver embedded in the particles. So if we could recover the silver from that silver nitrate, it would be useful and would actually be valuable. So the context is really just telling us a little bit about what could happen. We could recycle the silver from the reactant called silver nitrate by knowing the correct chemistry. So the first thing that we will do is we'll look at our available quantities, right? Our available quantities, 187 grams of copper is available. 387 grams of silver nitrate is available. If you look at part B, it asks, if these were the two available amounts, what mass of silver could we make? Look at over here, silver is on the product side, right? We want to know what mass of silver these would make when one of these runs out. So what we're about to do is we're about to use stoichiometry 2 times, once for copper, once for silver nitrate, and determine which of those makes less silver as a result. So if we're using dimensional analysis, again, the strategy starts with writing down the given. It may be a good idea to pause here and use the strategy that you are interested in using and see if you can predict what is limiting and what mass of silver could be produced as a result of running out of the limiting reagent. So recall that we're trying to produce the gram amount of silver, the mass of silver. So we're going to start with our dimensional analysis method. 187 grams, that's the given quantity of copper. We're going to turn that into a mole amount of copper. So the molar mass for copper, right from the periodic table, bada bing, we got a mole amount of copper now. What that will allow us to do is use mole ratio to turn it into the chemical we're interested in. Well, we're interested in silver right here. So we use the mole ratio to turn it into silver. Now we would have the mole quantity of silver. Next, what we'd like to do is we'd like to know, well, what mass of silver is that equivalent to? You simply use the molar mass for silver to do that. For every 1 mole of silver, there's 107.87 grams of silver. Mathematically, this would produce 635 grams of silver if we started with 187 grams of copper and all that copper was used up. Now we need to do similar stoichiometry starting with the other reactant, silver nitrate. So the first thing we do, molar mass, we turn this mass quantity into a mole amount, the amount of silver nitrate. Next, we apply the mole ratio. 2 moles of silver for every 2 moles of silver nitrate. What that will do is that will make it now a mole amount, but a mole amount of silver. So the number of moles of silver, recall we're trying to get to the mass of silver, the number of grams. So we add a final step. We use the molar mass of silver. There's 107.87 grams of silver for every 1 mole. We do the mathematics. You find out 387 divided by 169.87 times 2 divided by 2 times 107.87 produces 246 grams of silver. Looking at this, we now know what is limiting. The chemical that produces the less amount of product happens to be our silver nitrate. So silver nitrate would be our limiting, AgNO3, we would determine as our limiting. It makes less mass of silver. Let's take a look at the same mathematics using that other strategy, ratio proportion. Start out with your given over your desired. Given 187 grams of copper, we want to know how many grams of silver that could make. Fractions on the right have to match, grams of copper, grams of silver. What goes in front of them? Quantities equal to 1 mole, the molar mass for copper, the molar mass for silver. What we add to that, mole ratios. 1 mole of copper, no coefficient, equals 1. Coefficient of 2 for silver, cross multiply, x times 1 times 63.55 2 times 187 times 107.87 turns into an equation. Equation looks in this form. Divide each side by 63.55. We get 635 grams of silver from the other strategy, just like we did for dimensional analysis. Next, let's demonstrate ratio proportion using silver nitrate. Right, silver nitrate, 387 grams is given. We desire the number of grams of silver it could make. On the right side, the fraction should match, grams of silver nitrate over grams of silver. Recall what we placed there, the quantities equal to 1 mole. Since these are both mass amounts, we use molar mass. In a previous example, we used 22.4. Be careful, that's because that was a volume amount. So we have the molar mass for each chemical. We apply the mole ratios. 2 moles of silver, 2. 2 moles of silver nitrate, 2. Next thing we do, cross multiply, turn it into an equation. Cross multiply turns into this form of equation. Divide each side by 339.74. Bada bing, 246 grams of silver. So we can answer both parts of our question. What is limiting? Well, we've determined limiting happens to be the one that we run out of first, which is the one that produces less product. Limiting would be our AgNO3, known as silver nitrate. So we'll label that as limiting. What mass of silver would be produced? Well, the mass of silver that it could produce is only 246 grams because silver nitrate limits our ability to make any more. So the mass it could produce, 246 grams. Seems like a lot of work, but when you think about it, it really is just using stoichiometry multiple times. So that wraps up our lesson for the day, our lesson on how we determine what the limiting reagent is and how we determine what quantity of product we could produce as a result of running out of the limiting reagent. I hope you found today's lesson useful. Signing off until the next time, this is Mr. Brewer. Stay well.